Thank you, ladies and gentlemen. Welcome to Lemaitre's limits to our universes. Does anyone here remember this expression? I ask because there are a couple of problems, big problems with the Big Bang Theory, modern problems that we can solve by knowing our astronomical history, by knowing about Lemaitre's limits to our own particular universe. The problems I refer to are the fact that there is nothing beyond the Big Bang. All space and time are said to exist within, and only within, our own particular universe. But the bigger problem, too, is the fact there's nothing before the Big Bang. Everything in existence is said to have exploded into existence out of absolutely nothing. And of course, the idea of getting something for nothing violates, as you know, the conservation of matter, of energy, of mass energy, since the time of the ancient Greeks, Sir Isaac Newton and Albert Einstein, respectively. It is literally as though at its origin, the Big Bang Theory is saying this. Now, before we go any further, let's first pause and show some respect for the Big Bang Theory, because even with these problems, this happens to be the best theory explaining everything in our universe that we have ever agreed to. It accounts for the recession of galaxies, it explains the background radiation, the discovery of which won the Nobel Prize for Benzias and Wilson. It explains the distribution of the elements, and so you could say, with or without Lemaitre's limits, the Big Bang Theory we have, the standard cosmological model, as it's called, as it stands today, stands tall. Because to restate these only two problems that it has, the nothing beyond and the nothing before, one could say, well, okay, therefore, the Big Bang Theory we have explains everything in our universe. I mean everything, from right after its very, very beginning to literally as far as it goes. And so you should know that this very successful Big Bang Theory is fully incorporated within Lemaitre's limits. We miss nothing. In fact, we change nothing by adding Lemaitre's limits to our Big Bang Theory. In fact, you should also know that adding Lemaitre's limits to the Big Bang, really, again, it's not a change. It's, at most, you could call it an improvement. And we should appreciate the fact it's a very small, minor improvement. We couldn't be talking about a lesser leap, to be honest. We're actually finally biting the bullet here and taking the plunge, the leap, so to speak, and defining in better terms, at last, what comes beyond our universe and what came before. And to show you how easy this is, it couldn't be any simpler. It's literally 1, 2, 3. We're talking about a 3-sphere model of our universe as opposed to a 1-sphere model. And you can see, as promised, there's the expansion radius within Lemaitre's 3-sphere model. Technically, this is known as his dynamic equilibrium theory. As opposed to, on the right, you see the 1-sphere model we have today. And it's a bit of a one-trick pony in the sense that Einstein said a good theory should be as simple as possible, but no simpler. And the problem with the 1-sphere model is it cannot account for what that sphere is expanding out into, i.e. what's beyond. Nor can the 1-sphere model account for what that sphere is expanding out from, i.e. what came before. Whereas with Lemaitre's limits, this is easy, because he is, in addition to this one expansion sphere, simply adding this, always bring to the table, 2 other spheres. One outer sphere, an outer limit, and one inner sphere, inner and outer limits to the expansion radius. That's all that this involves. And it really, to define the outer boundary a bit better, Lemaitre is saying that the outer boundary is the Schwarzschild radius. You've heard of this, the Schwarzschild radius of the event horizon of a black hole. And then you can see that the expansion radius, technically the Hubble radius, operates within and only within that outer boundary. And then what's inside is even more interesting. This inner sphere, that's just Einstein's old static universe. You've heard of this. And to better define what the inner and outer boundaries are, all Lemaitre's limits is saying is that our Big Bang, our entire universe, exists within a black hole. And so all matter within our universe can never escape beyond this outer boundary. And then again, there's the Hubble radius, expanding within and only within that. And then what's inside here, Einstein's static universe, that's just a hollow, rotating, vacuum energy filled, dark energy filled, if you will, core. There's no mass, no matter in there at all, nor can there be, because it's all repelled out by the vacuum energy. And all that entails is, in fact, the core of Lemaitre's limits universe, is what the entire universe was believed to be, based on Einstein's first original solution to general relativity. And all that entailed was the fact that Einstein had had general relativity for a couple of years and had encountered the problem because it's a gravitational theory, that all his models just gravitationally crushed inward into a single point, until Einstein said in 1917, well, okay, therefore, all this matter and gravitational attraction must be counterbalanced by what he called vacuum energy, attributed it to electromagnetic repulsion, but it just results in a universe in perfect balance between gravitational attraction drawing matter inward on the one hand, and vacuum energy, electromagnetic repulsion repelling matter outward on the other. That's Einstein's static universe. That's an unchanging solution to the theory of general relativity, as opposed to the changing, dynamic, expanding theory that we have today in the Big Bang, originated by de Sitter, improved by Friedman, then Lemaitre, and then observationally proved by Hubble. But we should appreciate here, we have just seen in these last two slides, all of the possible solutions to our universe according to the theory of general relativity, in the sense that we're talking, there are only changing versus unchanging possibilities. So changing out of the dynamic expanding theory that we have today, as opposed to unchanging, the static stable stationary model that Einstein first proposed. And all scientists, typically Einstein included, believed the way our universe works, the correct answer according to general relativity, had to be just one or the other of these models. It could never be both. And the only scientists then and to this day, to my knowledge, who said, well, wait a sec, why couldn't you have both of these kinds of general relativity in a single theory? Why couldn't you have an unchanging, a static universe in the center of the universe, and that's surrounded by a changing, a dynamic, expanding, contracting part of the universe? And then even better, Lemaitre puts all of these possibilities, according to the theory of general relativity, into a nice, neat single theory, placing everything within the confines of the outer boundary of a black hole. And the beauty of adding Lemaitre's limits to the Big Bang is that with them we can solve problem one, and replace the idea of nothing beyond our universe with the fact that there must be multiverses beyond our universe, because if our own universe does have an end, a finite outer boundary, then by definition, in order for space to continue infinitely beyond that, there must be other universes essentially like our own in order to fill up that infinite space. So it allows the Big Bang to fit in with infinite space. Adding Lemaitre's limits to the Big Bang also solves problem two by replacing the idea of nothing before the Big Bang with the fact that there must have been something before the Big Bang, the vacuum energy. And it replaces the notion that our universe could ever have shrunk down to a size of zero, the so-called singularity, with the fact that it could only have ever shrunk down to a certain minimum size as defined by the vacuum energy core. So in this way, it allows the Big Bang to fit in with infinite time. Even better, adding Lemaitre's limits to the Big Bang allows that theory to avoid this terrible fate, this heat death of the universe you've heard of, where if expansion did continue unendingly, then everything in our universe would grow ever further and further apart. Everything would grow ever colder and colder, become increasingly isolated, alone, and dark. And that is not the fate for our universe. With Lemaitre's limits, expansion can only go so far and no further. Everything in our universe can only grow so cold and so colder. Lemaitre's limits is literally invoking the Goldilocks rule and saying our universe can grow not too cold, not too hot, but only just right. Best of all, adding Lemaitre's limits to the Big Bang allows for that theory to be a balanced theory, involving balanced expansion in terms of expansion out, contraction in, expansion out, contraction in. Those veterans in the audience who remember the cyclical oscillating models of our universe will appreciate Lemaitre's limits, as opposed to without them, what we have is unbalanced expansion, because it's all expanding all the time. That's all it ever does and all it ever will. and because that expansion proceeds in one direction only, not balanced. So that's what Lemaitre's limits brings to the Big Bang. We're simply, again, talking about an outer and an inner limit to the expansion radius. And by adding these, the ability to better define, A, what lies beyond our own universe, and B, what came before the Big Bang. Now, you can see I am passionate about wishing to resurrect Lemaitre's limits into the modern conversation when these issues of what lies beyond and what came before come up, as they still do. And all I'm asking of you, good ladies and gentlemen, in this admittedly hard road to hoe, is to consider Lemaitre's limits and judge for yourself whether they're not worth resurrecting, or at least considering. You could do this as easily as trying my very brief paper titled Lemaitre's Limit, published in the Journal of the Royal Astronomical Society of Canada, April of last year. Even better, you could learn all about Lemaitre's limits from Lemaitre himself. He published his dynamic equilibrium theory with these limits for his doctoral thesis in physics, which he earned at the Massachusetts Institute of Technology. And actually, not only can you access that thesis, about 50 pages, you can download it for free, thanks to MIT's DSpace. And finally, I would just like to remind everyone that these answers from our astronomical history to these big problems facing modern astronomers aren't answers that were just made up, for example, by someone like me, or written down on the back of an envelope 10 minutes before we all got here. They're answers that come to us from one of the most trusted names in all of science, arguably the most trusted name in the science of our universe, cosmology. That's Georges Lemaitre. That's our point. Thank you, ladies and gentlemen.